I'm going to start with my one key takeaway. So if you remember nothing else from this talk, remember it's hard to make things easy. Now, everyone probably knows this. You know, if it was easy to make things easy, our life would be a lot easier. But there we go. This is the story I'm here to tell today. So the title of my talk is Abstracting FPGAs in Python for Fun and a little bit of radio astronomy. My name's Andrew Bolin, and I write control software for radio telescopes. I would like to begin by acknowledging the Ngunnawal people as the traditional owners of the land that we're meeting on today, and pay my respect to their elders past and present. I know everyone does this, but we have a really cool artwork that I wanted to put in, so I thought it was worth repeating, as well as for the other reasons, of course. And as Emma mentioned in her keynote speech this morning, in astronomy we are building on the knowledge of Australia's first scientists and astronomers, the Indigenous people. In case you're not familiar with CSIRO, I've got the obligatory corporate seal slide here, also because I needed an extra minute in my speech. We are one of the world's largest multidisciplinary science and technology organisations. We have 50 sites across Australia and globally. We provide state-of-the-art national research infrastructure, and we deliver many billions of dollars of benefits to the nation every year. So, thank you. So, I assume most people in the audience are not radio astronomers, so I will give a brief high-level overview of a typical, I'll say typical, they're not all the same, but this is reasonably typical, radio astronomy signal flow. If I can find my mouse pointer. Okay, so starting across the bottom of the graphic, we have a radio source somewhere out there in the universe. It could be another distant galaxy, a pulsar, whatever. So those radio waves travel through space, and some years, billions of years later perhaps, reach our antennas here on Earth. The signals are then digitized, transformed into ones and zeros, sent along to something called a correlator or a beamformer or both. And I'll explain that in a minute. The outputs from these usually go to a supercomputer for further processing. And the results from the supercomputer come back to our friend the astronomer at the top of the screen. And the astronomer also gets to drive the telescope. Now, I've represented here a telescope control system as one block, but in reality it's many pieces of software all working together. It's a distributed control system driving all these different bits. A lot of it's real time, some of it is offline, asynchronous processing. So I've worked on a couple of different projects in a team that specializes in building correlators and beamformers. Specifically, the bits that I focus on are the layers between the signal processing hardware and the control system. The little yellow circle, that's me. And I should say it's not just me, there's other software engineers as well. So there's a lot of people involved in these projects. And the main project I work on, you might have seen JC's talk on the opening day about the Square Kilometre Array. I work on something called SKA-Low CBF, which is the Square Kilometre Array, low frequency telescope, correlator and beamformer. So the low frequency telescope covers 50 to 350 megahertz. It's being built in Western Australia. Hopefully when it's finished we'll have 512 stations. And low CBF, under the full telescope, will process about 6 terabits per second of data input, producing about 9 terabits per second of data output. And we can look in different directions at once, we can do all kinds of things in parallel. Now I said I would explain a correlator and a beamformer. This isn't a maths lecture, I'm not an expert on these concepts. I'll try and give a quick overview of what these things are so you have some idea of what I'm talking about. I'm going to start with the beamformer first because it's much simpler. So a beamformer, as you might guess from the name, forms a beam. In other words, it looks in a particular direction. And the way that we do this is by time shifting signals. This concept is used in lots of common radio equipment, mobile phone towers, Wi-Fi, extensively in radar and military applications. But if we imagine these blue dashed lines are radio waves coming in from space, so they're following this grey dotted line as the direction of propagation, they're going to hit our antenna on the right first. So it needs the longest delay. I've represented that by 3 hourglasses. The radio waves next reach this one, and finally this one. So by the time the radio wave has gotten to that last antenna, it needs no delay. Everything's now aligned. You sum them all up, and you get, effectively, it's as if you've got a giant parabolic dish pointing in the direction of that dashed line. You can't do this in Python, but in Julia, I believe you can actually define an emoji as a variable. So you can have hourglass equals 2 pi on lambda d sine theta. Correlator is a bit more complicated, as I said. So here we take each pair of antennas or stations, and we cross-correlate the signal at each pair. So each of these pairs is called a baseline, and the cross-correlation of these produces something we call a visibility, which is a complex number. In other words, it's a magnitude and a phase. Now these give you information for a particular spatial frequency and orientation that contributes to an image. If you know about JPEG compression, you might know about the discrete cosine transform, and it has spatial components in the image. Very much the same concept. What else have I got to say here? So the images are created using many of these correlations over time. You've probably seen long exposure photographs of the sky where you see the stars form a circular trail. So we take advantage of this fact to get different orientations as the Earth rotates. So each pair only gives you information in that one spatial direction. For example, the purple dashed line here will give you fine image detail in the horizontal axis. So output data for a correlator is proportional to the number of baselines. The equation is stations times stations plus 1 divided by 2, which you can approximate by the square of the number of stations, proportional to the number of the square, I should say. So our data rates get very big when we have 512 of these things. It's massive. So for this reason, low CBF is being installed in the Pawsey Supercomputing Center, and the data will be processed on its own dedicated supercomputer, which we call SDP, Science Data Processor. How do we do all this maths? We use FPGAs. Does anyone not know what an FPGA is? Raise your hand. Good, some people weren't scared off by the title. An FPGA is, the acronym stands for Field Programmable Gate Array. So it's essentially a large, very large block of customizable digital logic. It's as if you've got a chip that does whatever you want to do, but you don't have to pay $1 billion for TSMC to make it for you. Yeah, some of them are relatively cheap, some are not. So the ones we use is this AMD Alveo V80. I don't know if the list price is public, so I won't mention it, but it's not cheap. It has 4 very high-speed Ethernet interfaces. It's got a bunch of high bandwidth memory. The PCI Express edge connector you might be able to see on the bottom there, we only use that for control. No astronomical data flows through the edge connector, only control signals. We're currently running 100 gig Ethernet. Work is underway to upgrade to 200 gig. We control this stuff through a software tool called ARGS, Automatic Register Generation System, which generates some of the FPGA configuration and a hierarchical map of register addresses for the software to use. And it comes out in this monstrous nested dictionary Python file. So to read an address, this is the naive way to read an address using an ARGS interface. You look up your peripheral address, you drill down into that, you find a start address, you find an offset for the particular field you're interested in, and you say driver.read base address plus offset, 1 value. Writing, almost the same thing. The only difference is you have to supply a value to write. Okay, but all this code is ugly and repetitive. I want my job to be easy. I don't want to copy paste this thing and do the same stuff all the time. I've said I want my job to be as easy as possible, but I probably should have written practical. I'm not super lazy, I just don't like doing annoying busy work or rework, probably like most of us. So I had an opportunity. There were 2 projects underway with about 5 different types of firmware to control. And I thought to myself, I like to reuse code, and I really like readable code. So when we had this change in a hardware platform, this was a great opportunity for a fresh start. So my goal was to create an abstraction layer for the control of the signal processing hardware that's both easy to use and to reuse. And I had some design principles in mind when I started this work. It had to be control system agnostic. We need to bolt different layers of software on top because people change their mind or it might get reused somewhere else. I want to have code reuse between different applications. We have all these different applications that a lot of them are doing beamforming but with slightly different parameters. So why should we reinvent the wheel? You know, just supply some different parameters. I wanted to have a consistent interface style, so the software would look similar. I like to provide sensible default values, so less typing. You know, if the default's good enough, you don't have to say use the default, just it's there. And I put this one in blue because I really like tab auto completion. Maybe, maybe I am really lazy. So I wanted to be able to type in, you know, the first few letters, press tab. Yes, that's what I'm looking for, great. I don't have to remember stuff, this is perfect. So this is the kind of code that I had in mind that we might be writing to control our FPGAs. We'd have an object that represents the FPGA personality, we call it, a particular application. An object that represents the peripheral, which is a module of functionality within the FPGA. And then we call a configure method, and we say destination IP address 10, 11, 12, 13. So how would this work? So as I mentioned, we have this FPGA personality object. It represents one FPGA image or application. And its job is to map peripheral objects to FPGA peripheral names. So as I said, a peripheral is a functional block within the FPGA design. There might be multiple instances within an FPGA. You might have the same thing 3 times. Different applications use different peripherals. And so then we drill down further, and how does this configure method work? So we have a peripheral class that implements abstractions for a particular FPGA peripheral. So if we look at the configure method, if I can find my pointer. So it sets a destination IP address property using the destination IP address string. And it sets a rate register by taking a rate, which is optional, it defaults to 100, clamps it to the allowable range, and sets a rate register. The destination IP address is itself another attribute defined in the Python code. And you can see here it takes the string, the IP address, converts it to a binary format, and puts it into this is a memory block at a particular offset that's stored as a constant. So all the user sees is configure destination IP address, and we've got this nice way of encoding what goes on behind the scenes to make that happen. So to make that happen, we have some magic. If you're not familiar with Python terminology, these double underscore methods are sometimes called magic methods. So at startup, each FPGA peripheral object discovers what fields it has via that massive args map dictionary thing that we saw earlier. And it has mechanisms to delegate the reading and writing of fields or registers to underlying field objects. I'll just mention here that all the code you see on the screen is massively simplified. I've taken out error handling and edge cases and whatever else. So we'll just see the meaty bit. You can see here when you get an attribute from a peripheral, it simply looks it up in its list of fields and returns that object. And when you try and overwrite an attribute, it says, no, I'm not going to let you overwrite that. I'm actually going to send that to this value parameter. which we'll see in a second. So next level down, we have these ICL FPGA field objects, and most of the magic there happens through this value property. So it has the code you probably guess it has, driver.read, address and length. And then if you try to set that property, it calls driver.write with an address and a value. The observant among you might notice that the length argument is missing, because in Python we can figure that out. If it's an integer, it's length 1. If it's a list, it has a length. So we don't need to pass that through. I should explain the acronym here. ICL is an acronym we sometimes use to mean instrument control layer, or in other words, the software that's controlling the FPGA. So this ICL FPGA field object represents a single FPGA register or a memory block, which is represented as an array. And it holds our information from the register map. It's got a human readable description. You know, this is the bit that turns on the thing, or whatever the FPGA engineer decides to write in there. Sometimes it's an essay, sometimes it's a cryptic acronym, who knows. It has its address and length, obviously. There's a couple more parameters that are used for bit fields, an offset and a width, so you can pack multiple values into one register if you really want to. You don't need to, because you've got 2 terabits of address space, but the option's there. And this inherits from another class called an ICL field class, which is used for the derived peripheral properties. So if you mash 4 registers together to combine into one thing, they don't have an address as such. So anyway, implementation details. So to recap that in the other direction, from the bottom up, we have ICL FPGA field, representing a field. It knows its byte address, and it has access to driver read and write through its value property. FPGA peripheral exposes each field, and FPGA personality exposes each peripheral. Now, a side note on flexibility. This definitely wasn't because I was indecisive. It was flexibility. These classes expose their contents as both attributes, which is in Python means the dot syntax, and as items or array index syntax. So you'll see code snippets that use both. How do we interface to a control system? That's quite simple. To bolt on a control system, we just iterate over each peripheral and the attributes and methods that are configured to be exposed for those. So as I mentioned, the ICL field objects contain a human readable description, and also parameters such as whether a control system should allow it to be written by a user or not. So this is made up code, very hand wavy, but essentially you write an add attribute and an add method function that suit your control system, and you just run a couple of loops and you're in business. In the SKA project, we use Tango controls for our control system, and in Tango it has these things called device servers, and a device server has attributes, which are similar to Python attributes or parameters, and commands, which are pretty much methods. So we've got it easy. In other telescopes, for instance, there's a control system called EPICS, which only works in key value pairs. So they have a bit more trickery they have to do to expose a method. They make each parameter a key value thing, and then they have a special one that says trigger this method. So it can be done. Tango has a web user interface called Taranta, and this is a screenshot of one of our FPGA things in operation. So it shows the attributes from a peripheral called speed SPS. And it has an enable signal, a bunch of standard Ethernet parameters, and a packet sent counter. We also have a command line interface. So because the code is independent of the control system, we can treat the command line as a control system. We can easily bolt on an IPython shell. So we have a command here, FPGA-device86-firmware filename -C for console. It can also do some other tricks, such as loading register values or executing a Python script, and supports multiple FPGA cards at the same time. So this gives us easy interactive tinkering. You can just type in FPGA. You don't even have to type FPGA. You can type fp_tab.system.ethernet rx total packets.value, gives you this massive number. You can write to FPGA LFAA reset, set it to 0. As I said, you've got tab auto completion. In IPython, it's really good. You press tab and it's got the list. You can scroll around and find the one you want, because if you're anything like me, you don't remember what the difference between these 7 things with similar names are. So the FPGA engineers really liked this. One of them said it's the best they've ever seen. I don't know if that's because they've not seen much or because it's really good, but I'll take it. And we also have access to the other parameters of these objects. So as well as its current value, we can see that this uptime counter lives at address 48, and so on. So at this point, I'm thinking to myself, this is great. Got readable code, reusable modules, and we've got a nice debug console. Let's hand the software over to the users, and let's see what happens. So what I found was software along these lines. Save addresses will access. We store a shortcut to a peripheral, and then we get this register and ask for its address and store that in a variable. And then we're calling driver.write and setting that to 1. Okay. What I thought I would see was LFAA decode.reset. So I expected an abstraction per peripheral. What I found was an abstraction per personality. I expected people would ignore addresses, but here they are, storing the addresses. I thought surely everyone will use magic driver operations, but no, here we have explicit driver operations. At least we all agree that you should only define your mathematical madness once, so it's in one place, so we're happy there. But it's quite different to what I expected. So how did this happen? It turns out that other people think differently. And of course, this is a good thing. You need different perspectives to come up with good designs. They're not always anticipated. There's another very specific reason, which is optimization. So in our previous generation FPGA, each register transaction took about 3 milliseconds. So that might be slow for some people. You don't necessarily want to do everything one at a time. If you have 16 error conditions to check, that could take you 48 milliseconds. But if those error conditions are all in sequential registers, you can just read 16 registers in about 3 milliseconds and be done. So this is actually a sensible time saving. Now, there were alternatives to do this in a way that I would call neatly. You could use a Python context handler to provide a list of registers that you cared about this time. You could modify the driver object to do some sort of batched reading. You could put a layer above the driver object to batch things or poll things or whatever. And in fact, one earlier version of this software did have a concept that I called adapters, where you could plug something in to do this very sort of polling or caching. But we removed that because it was too complicated. So why didn't one of these neat approaches get used? So the author was working in a different repo, of course, and no one wants to do 2 jobs when they can do 1 instead. It takes more time. There's a learning curve. It's painful, especially, you've got Jira tickets, you've got administrative overheads. Let's just do something that I can do now, use a workaround. But worse than that, I kind of accidentally told him to. So I got a message, hey, how can I read multiple values in one go? I said, actually, that's not implemented in the abstraction layer. Here's a quick hack. You could just do driver.read. But, it'll give you raw values, but, oh, thanks. Off they go. You're probably familiar with this quote, there's nothing more permanent than a temporary hack. So this concept of reading sequential registers in batches is actually, it's only rarely used. I forget how many actual uses, but it's not super common. But this method of storing addresses and doing what I say is bypassing the abstraction layer is actually very widely used. So 2 of our 5 implementations write the code like you saw. On contact with reality, you inevitably find more sharp edges in anything you've built. If you run a lint check on code that's written the way that I intended, it's angry. It says, you write something self.enable, you've got this register called enable, and the lint checker screams at you, hey, instance attribute enable is defined outside init. It's not really, but it doesn't exist until runtime, and the lint checker has no way of knowing about it, so it's upset. And we don't have our tab completion in our IDE because the same reason. We don't have the map when we're writing the software, it's only loaded at runtime. So we have to remember the names of everything. At least the first time. If you're using a good IDE, once you've written something once, even if it's outside init, it'll still tab complete the second time. And sort of following on from this, typos become a trap. If you accidentally press Z instead of A and you set self.ensbl to 0, there's no error, not even at runtime. Python just says, oh, you want a variable called ensbl. Okay. The linter doesn't help you. It gives the same complaint whether you spelled it right or wrong. So it's a trap. It's a trap that we can detect though. And so now we can log a warning. If you try to write to a register that doesn't exist, it will say, hey, that's not an FPGA field or defined attribute. We're going to create a variable. If you really want to create a variable and suppress this message, just put an underscore at the start, Python convention for protected variables. So let's review my design principles that I wrote down in the documentation at the start of this project. Control system agnostic, tick. We've successfully split the FPGA abstraction away from the control system interface. We've seen that in practice. Code reuse, partial success. There is some, it could be better. I might put some of the blame on the FPGA engineers here, that if their peripherals were more consistent, it might be easier to reuse software that interfaces to them. But we'll take that as a partial. Consistent interface style, yeah, that lasted about 2 days. Even among the code that I wrote. So some of it uses a centralized configure method like we saw in the earlier example. Some uses a bunch of properties that you set individually. Other authors have taken other approaches. Some of our newer code does use an abstraction class per peripheral, but it's not derived from the FPGA peripheral class, and it uses a separate scheme to instantiate and connect itself to the FPGA peripherals. So we'll give that one a big red cross. Sensible default values. Now, this is a tricky one. A lot of the stuff that we do in the FPGA does not have a sensible default value. When you're beamforming, you don't know. There's no ISO standard for how far apart your antennas are. You have to know. So we can't put a default in there. In some parts of the code, especially in the self-test tool we have that generates simulation packets, I do use a lot of defaults, and I think they're sensible, and that does work well. And my friend tab auto completion is unfortunately marginal as well. It works really well in the debug console, not so well in the IDE. We need to write things manually the first time. So sometimes I copy paste things from the debug console to make sure they're spelled right. What would I do differently? First thing is try and make things compatible with a lint check. All right, those lint warnings, they are there for a reason. Someone probably smarter than me has put that there because they've been burnt by it in the past. And it turns out that yes, we got burnt by it too. We had at least one really annoying to find bug that turned out to be someone had misspelled a register name and there was no notice of it. So to achieve this, if necessary, you could consider splitting out interactive conveniences for the console into separate code, perhaps if you need to. People might be familiar with the Zen of Python. Explicit is better than implicit. So I would make slow transactions explicit. One of the reasons people stored these addresses and explicitly called the driver methods is because they want to know which bits of the code are going to be slow. So if we make that explicit, rather than doing too much magic behind the scenes, people can see, this bit of code is going to take time. It's doing a transaction to the FPGA. Using methods like this also prevents spurious reads when you copy objects, which can happen in the current implementation. I would also have some mechanism to explicitly declare the required fields. So this would probably help with our linting checks, and it would definitely help with FPGA compatibility checks. If the FPGA engineers have renamed, added, or deleted fields, sometimes you want to know about that. If your enable field is now called activate, your code's not going to work. So if we explicitly define the fields we need in the init method, for example, we can check that they all exist at startup and flag an error. I don't know exactly how to do this, but the concept is good. So I wouldn't bother implementing operators. I implemented all the operators. Add, multiply, left shift, XOR, power, you name it. You might notice that you haven't seen that before in this talk. That's how little it gets used. I had this grand idea, someone might want to write peripheral.foo equals peripheral.bar times peripheral.baz. Nope, no one has ever done that. So this is an example of the you ain't gonna need it principle, which you might be familiar with. Another one is to, maybe talk to people, ask the users what they want. If I'd asked 3 people, it's probably likely that batch read would have come up. It's not an uncommon thing to want to do. I would also avoid quick hacks, even for experimental use. Or at least I wouldn't tell people about them. So if my colleague had said, hey, how can I read multiple values in one go? I could have said back, it's not implemented in the abstraction logic. Let's meet up and discuss the best way to do this. We might have ended up with some shinier code. But overall, I think this has been a success. The software is in use. We've applied it to 5 different FPGA personalities across 3 different projects. It's facilitated easy FPGA hardware updates because it's separated the driver layer from the abstraction logic. So we've been through 3 different hardware platforms, multiple different drivers as well, OpenCL, Xilinx runtime, the new AMI with some disturbing nested acronym, whatever that stands for. And along the way, of course, I've learned a lot. We're here at everythingopen. Where's the code? It's on GitLab. The SKA telescope stores all their code on GitLab. If you search for low CBF FPGA software interface, you'll find it. There's the address. And it's released under the CSIRO open source software license agreement, which is basically the 3-clause BSD license. So coming back to my main point, it's hard to make things easy. It's hard to do, but ultimately, I think it's worth it. Hiding all the boilerplate code means that the code that actually does the control stuff is much easier to read. Making an easy-to-use debug console means the firmware engineers are more likely to use it. It means they don't ask me for help so much. Now, I think I've still got a few minutes here, so I have a little bonus side quest here, which I called FPGA as a file system. Again, the software is modular and designed to be control system agnostic, so we can treat the file system as a control system. So using Fuse, we can bolt this on pretty easily. So here we see our peripherals represented as directories, CMAC, DRP, etc. And then under the system directory, we can see a whole bunch of FPGA registers. And we can read these using cat. Proof here that it works, that the time changed between runs of cat. We can even encode some magic in the back end to change the representation of different fields. This magic number was chosen to look like vaguely like the word FPGA tool in hex, kind of. And we can also read our abstraction. Like, it doesn't just have to read raw registers. We can read the firmware version, which is combined of about 5 or 6 different registers to get this string 0.1.8-main-.hash. And we can see that we're talking about, if that little thing would go away, a personality called Scenic, customizable network interface card. It's a test tool that we have. And of course, you can also write. When you figure out the right file system hooks to implement, you can see here that we read the value. It starts as 1, echo 0, read it back, it's now 0. Yeah, so that was a fun little addition to do as well. All right, that's the end of my slides. Thank you for your attention.
Thank you very much for your talk. Do we have any questions?
Thanks for that. Are the args definitions, are that all coming from your FPGA folks, or is that a centralized?
Yes, it tends to be written by the FPGA engineers, and it's actually specified in YAML files that then get transformed into VHDL to implement the FPGA side of the register access, and then that map that you saw.
Do you get much collaboration with the kind of open source, like the FPGA tool things like Glasgow interface thing, and that's all Python as well with FPGAs?
No, we don't. I've heard of these open source FPGA things, but because we're crunching so much data, we have to use the biggest and best chips, and they're not supported. So we have to use the vendor tools to get access to that.
Any other questions?
Thank you very much. A very impressive talk. I know it's an abstraction layer, but did you burn out any FPGAs? And the second question is, I'm very motivated by your software layer because I would like to do a lightning talk on self-driving devices. And so since you have a hardware controller, software, I could use that for my pet project as well. So have you burned out any hardware accidentally because of someone else, other operator?
I don't think so. No, some of the other radio astronomy groups in other countries have tried to not use the vendor-provided interfaces, like over the PCI bus, and tried to flash their own stuff, and I know they have bricked some cards. I don't think we bricked any. We have gotten them into broken states, like these cards assume that you're in a server with a leaf blower on the front of it blowing air through it, so we've had some strange errors that turned out to be things melting, well, not quite melting, but shutting down to self-protect. Yeah, but no permanent damage that I can remember.
So you could move on from FPGAs to other hardware?
Conceptually, sure, yeah. Yeah, so I should also mention the args thing there is also modular, so it doesn't have to be args, it's just that's what it is. You can bolt other things in.
These FPGAs you're using, how many cells do they have, and approximately how much do they cost, if you can say?
I don't know if I can say. I actually don't know how many. Yeah, what is the?
So that was
Okay.
9,000 US.
$9,000 US a pop, yeah. I don't remember numbers, sorry.
So you gave an overview of all the Python
you made and like, which bits were useful or not useful. So the file system API you made, like did that end up, was there a similar sort of takeaway of which bits of that were useful, or was that kind of for just some extra debugging? Or
It was just it was there. Felt like learning about Fuse a bit, so it was just it was a toy.
Yeah, fair enough.
Yeah, no real application there, but you're probably familiar with the Unix concept of everything as a file. So I kind of had in mind, maybe this is the way it should have been, I'm not sure. So yeah, it was just a learning exercise.
We've got time for maybe one more quick question.
So maybe I'm not super clear on where ARGS fits into the FPGA design area, but one of the things we've been struggling with is what the effect of different layouts of the blocks on the FPGA does to space usage and latency between all the signal propagation. Is that something that we could simulate using some of these tools, or is that more of a low-level analysis that you do first to write the ARGS baseline to then use this tool to control?
Yeah, so the ARG system on the FPGA side just does like the register interface. It's not implementing signal processing stuff. Can this simulate placement things? No. It can simulate an FPGA register interface. So if you have software that you want to test without hardware, you can test your control software to a certain extent. Obviously, there's no real hardware to drive, so you can't do much meaningful things, but you can test it to a certain degree. Yeah. FPGA placement, it's a dark art. The FPGA guys do all that, constraints, super logic reasons, all that stuff. That's their ballpark.
All right, thank you for a wonderful talk. I hope everyone got some useful things out of that. We have a small speaker gift for you.
Thank you.